Hybridization theory is a very useful method for understanding electronic structure of molecules. Typically, what's taught about hybrid orbitals, especially for undergrads, is just sp1, sp2, and sp3 orbitals in organic chemistry. In some cases, it seems like this leads to some confusion. What are hybrid orbitals? Why are they useful? Here, we'll talk a little about what they are and how they're generated at the introductory level. In a future video, we'll talk more mathematically about generation of hybrids and some simple equations that can be used to get more information about compounds, but we'll keep things pictorial here. In organic chemistry, your first introduction to hybrids may involve a discussion of the angles between groups. You'll learn that methane is tetrahedral, for example, meaning the hydrogens sit at the vertices of a tetrahedron. The way hybrids get used in introductory organic classes is relatively simple. You're taught that carbon always makes 4 bonds. The bonds can be single, double, or triple bonds. A single bond has a sigma bond between the groups. A double bond has 1 sigma and 1 pi, and a triple bond has a single and 2 pi bonds. If all of the bonds are single bonds, there are 4 things attached to carbon, like the 4 different hydrogens in methane. This gives an sp3 hybridized carbon with a tetrahedral structure. In order to just have 4 bonds, all the bonds are single. 1 plus 1 plus 1 plus 1 equals 4. The HCH angles are then 109.4712 ... degrees. The tetrahedral angle is an irrational number with a non-repeating infinite series of digits. If there are 3 things attached, then the carbon is sp2 hybridized. To get to 4 bonds in this case, we have 2 plus 1 plus 1 equals 4. 1 double and 2 single bonds. This gives a flat carbon with 120 degree angles between groups. An example would be the carbon in formaldehyde. If there are 2 things attached with 1 single bond and a triple bond, so 1 plus 3 equals 4 bonds, then the carbon is sp1 or just sp hybridized. This gives a linear carbon with a 180 degree angle between groups, such as in acetylene. Alternatively, you can have 2 double bonds to the same carbon to get to 4 bonds. With just 2 substituents, this carbon is also sp hybridized. This happens in things like carbon dioxide. In sum, if the carbon has 4 things attached, it's sp3, tetrahedral, and the angles are 109.5 degrees. If it has 3 things attached, sp2, trigonal planar, and 120 degree angles. If there are 2 things attached, it's sp hybridized, it's linear, and they're 180 degrees apart. The above is generally true and can help you understand the geometry of carbon in organic molecules. But let's dig into why this is the case a bit more. You can think of the hybridization as changing because of the types of bonds. With s and p orbitals, one can make 2 kinds of bonds. You can make sigma bonds and pi bonds, which are differentiated by the number of nodes parallel to the bond axis. A node is a place where the phase changes from positive to negative. In other words, it goes through 0. Sigma bonds have no nodes parallel to the bond axis, and both s and p orbitals can be used to make sigma bonds. Here, the dots in the electron clouds are meant to indicate the positions of the nuclei. The phase is the same as you rotate around the line between the 2 nuclei, so this is a sigma bond with no nodes. If you combine 2 p orbitals, where the lobes are pointed directly at one another, you can also make a sigma bond. Again, if you rotate around the internuclear axis, the phase doesn't change, so it is a sigma bond. The above are the bonding combinations. If orbitals of the same symmetry but opposite phases are used, it is still a sigma bond because there's still no change in phase as you rotate around the internuclear axis. In this case, there's a node between the nuclei, which makes this a sigma antibonding orbital, a sigma star orbital. What hybridization does is mix s and p orbitals to form sp hybrids. Because we are starting with 2 full orbitals, we will get out 2 hybrids. Pictorially, we could draw something like this where we sum the orbitals together. The side with the same phase will get larger, and the side with the opposite phases will cancel somewhat, making it smaller. In other words, the shaded lobes constructively interfere to make larger shaded lobes, and the shaded s orbital and unshaded lobe of the p orbital destructively interfere to make a small unshaded lobe in the hybrid. Notice we don't change the direction of the p orbital as we make the hybrid. Mixing with s won't change the direction because the s orbital is spherical and highly symmetrical. Above, we just got 1 hybrid. To make the second orbital, we change one of the phases and mix again. Let's change the phase of the s orbital. This time, the light-colored lobe will become larger, constructive interference, and the dark shaded lobe will become smaller, destructive interference. Again, the p orbital doesn't change direction mixing with the s orbital. As a result, we have two orbitals with their large lobes pointed 180 degrees apart, ready to bond with groups near the carbon. If we bring two p orbitals together side on, then we can generate a different kind of bond, called a pi bond, with one node along the internuclear axis. Maybe it is obvious, but there's no way to make a pi bond with an s orbital. The s orbital only has one phase, so there's no way to get this type of bonding. Carbon must use a pure p orbital to make a pi bond. The hybrids with s character are used to make sigma bonds only. If there is a double bond, there's one sigma bond and one pi bond. A sigma bond can be made with any type of orbital, s or p orbitals, but also d, f, and g orbitals for that matter. However, an s orbital can't be used to make a pi bond. As you introduce pi bonds, the number of p orbitals available to hybridize decreases because the pi bond requires a pure p orbital for its existence. The hybrids, which have s character, are used to form sigma bonds only. If you have no pi bonds, you can have a tetrahedral sp3 hybridized carbon. There are 4 equivalent sp3 orbitals on the carbon, and you can bond to 4 groups. For example, 4 hydrogens to make methane. If you have one pi bond, you lose one p orbital, so you have an sp2 hybridized carbon, and can bond to 3 groups with sigma bonds. If you have 2 pi bonds to the same carbon, then you are sp-Hybridized and can only form 2 sigma bonds 180 degrees apart. This is why CO2 is linear. As a quick quiz on this sophomore organic level hybridization theory, let's look at a few common molecules starting with benzene. All of the carbons in benzene are equivalent, so if you pick any carbon, what hybridization is it? Keep in mind that each carbon has a hydrogen as well, so there are 3 sigma bonds. Because the carbon has 3 sigma bonds, the hybridization is sp2. What about the carbons in pentane? You add hydrogens to get to 4 bonds on each carbon. There are 2 kinds of carbons in pentane, methyls, CH3, and methylenes, CH2. However, they are both sp3 hybridized because they have 4 different sigma bonds. Let's do one more. How about 1-phenylpropyne? Again, it may help to add the hydrogens, but if you stared at enough structures, you may not need to. In this case, there are all 3 different kinds of hybrids. The carbons with 2 sigma bonds are sp, the carbons with 3 sigma bonds are sp2, and the methyl carbon with 4 sigma bonds is sp3. In the next part of the series, we will show in more detail how hybrids are formed and the important relationships between them. In introductory organic classes, it is common to talk about average hybridization of the sigma bonds to an atom and say things like the atom's hybridization is sp3. In reality, an atom may have orbitals of different hybridization, and that can be useful information about the structure and bonding. Thanks for watching. We make these videos for fun and as a way of giving back to the community. If you enjoy the video, please subscribe and give us a thumbs up. Really, the best way to support our channel is to watch more videos, and we have quite a few up at a variety of levels. Thanks again.